So when dealing with crosstalk in your PCB designs and stack-ups, there's a couple of parameters that are important to understand and that you can work with to reduce your overall crosstalk. So in terms of crosstalk, what happens is you have two traces next to each other, you have two signals driving energy, and they couple next to each other, okay? And really the coupling between these two is both capacitive and inductive coupling. And so, of course, when you look at this, the easiest way to reduce crosstalk is to separate your traces from each other, right? So if you've got two 5 mil traces and there are only 5 mils in between them, that's pretty tight coupling. But as you go 10 mils, 20 mils, as you separate them too, the coupling is so weak that essentially there's no impact from crosstalk. So increasing your trace spacing is the biggest thing that you can do to reduce your overall crosstalk. Now, this comes at the cost of board real estate. You can't realistically use in a lot of dense designs too large of a trace space. You can't have 50 mils in between your traces. You'll never be able to route your boards. So you really need to use simulation and some other types of analysis to determine what the right amount of spacing is between your traces in terms of your link margin. And I really don't want to give a generic rule of thumb here. You really need to do some simulation analysis to determine that. But just remember that, roughly 1x the trace spacing distance is really not sufficient. Some people like to do 2x or 3x as a general rule, but again, you really need to do the design and analysis to figure out what the right spacing is for you. Now, another thing you can do is reduce the dielectric height. So, for example, let's say you have a microstrip trace, and then you've got some FR4 dielectric material acting as an insulator between, say, a ground plane. Now, if it's 3 mils versus if it's 10 mils, that's going to change the coupling right from your top trace down to your plane. And as you lower that dielectric, so as you make it thinner or you make it smaller, it more tightly couples to your reference plane, reducing the overall coupling, and that has an impact on reducing your crosstalk. So that's another thing you can do. But again, that's not something that you have a lot of control over, because as you change that dielectric height, that thickness, you're also going to change your target impedance, right? So if you're using a 4 mil dielectric height for a microstrip trace that's 5 mils wide, for example, and let's say that did give you a 50 ohm impedance, if you were to make that thinner, you would essentially have to make your trace width either thinner or wider itself to compensate in your impedance formula. So trying to use the smallest dielectric height you can, while it'll help you with your crosstalk reduction, it's not always applicable or realizable in your design. The last thing to consider with crosstalk is, remember, you have to have a trace next to it in order for the energy to couple. So that coupled length, in terms of how you route your interfaces, can impact the crosstalk as well. And this does sort of get into a couple of different types of crosstalk in terms of what we call backwards crosstalk or near-end crosstalk and forward crosstalk. And the difference between the two is near-end crosstalk immediately impacts next to the driver that it's driving, where far end goes down the line to the receiver, if you think of two drivers next to each other. And one of the biggest differences is near end crosstalk saturates pretty quickly, right? So if you think of it as a driver being right next to each other, the coupled energy there can saturate pretty quickly. So it really doesn't matter how much of that coupling you have next to it. It's really more a function of the coupling coefficients. But forward crosstalk, since it's got to go down the line to the receiver, the longer you run those parallel traces, the more it's going to build up, and up. So for reducing things like forward crosstalk, reducing the coupled length that they are together will help reduce your crosstalk. In terms of reducing your crosstalk for near end, it's not so much about the parallel length, but reducing the spacing and also reducing your rise time and other things like that affect your crosstalk can help reduce it as well. So there's a couple of things with crosstalk and how you can reduce them in your stack up, and a few things to think about when you're designing your stack up for crosstalk. Thanks for joining me today for this coffee break video. I hope you enjoyed it. If you have any questions or feedback, or if you have a topic that you'd like me to discuss next time, send me an email at tim@signalbytestech.com. And be sure to join us online at signalbytestech.com. Sign up for our newsletter, be notified when we do another one of these videos. Now, I'm going to have another cup of coffee, and it's probably time for you to get back to work. I'll see you next time.